It's time for show and tell. So I have here my breadboard, and the H-bridge circuit is absurdly simple. I have 4 NPN transistors. I'm using 4 resistors for inputting the signal. So this circuit is assuming that the input has no impedance or very little impedance, which for the oscillator is true because that's an open collector setup. And for the bench power supply is true because it has no unavoidable impedance besides the inner workings. It just turns down the voltage if you exceed the current limit. I am using 220 ohm resistors. The reason for this is I want these to be as small as possible, first for the best responsiveness. Now, obviously at the frequencies we're working at, that's immaterial. But just working theoretically here, for the principle of the matter, less resistance is more responsiveness to changing voltage. So smaller resistor, better response. Second, I want to make sure, because these are supplying the base current, I want to make sure that they're always supplying enough base current to completely open the transistor to put it in saturation, regardless of how much current we have going through the transistors. And finally, I want them to be as small as possible so that they take as small of a voltage drop as possible on their own, so the load has the maximum amount available to it. The transistors I'm using are the most powerful ones that I have available to me. They are the 2N222A NPNs that can handle a maximum of 800 milliamps through the collector. They have high voltage limits. They can dissipate 0.625 watts and a frequency transition of 300, whatever that means. I assume higher is worse because generally, according to this list, this fine little list I have here, the higher the power that can go through this thing, the higher the frequency transition. The ones that have small numbers like 80 can only take 150 milliamps. So generally that kind of trade-off, it's like Schottky diodes. Schottky diodes have a lower forward voltage drop than regular diodes, but they also handle less power. So it may be something similar anyway. I'm using those to make sure if I want a lot of current through here, like if I'm powering a motor rather than a signal, that it can handle it. And as a reminder, I'm not using any resistors at all through the transistors, through the collectors and emitters, because the switching should be happening quickly enough. As long as I never supply a signal of high to both sides, should be fine. It'll go over the power limit for brief instance, but that's just going to generate a little excess heat, and then it'll dissipate. It should be fine. And then I have my oscilloscope probe plugged in here. So let's very simply wire it up. I'm going to say that these 4 runners are the 4 signals. So we'll say signal 1 goes through a resistor, and that goes into the base of the first transistor. This is the top left in the usual circuit diagram. Signal 2 goes through a resistor, from there into the base of the second transistor. And furthermore, signal 3 through resistor 3 out of there, and this is the top right, so on the other side, the first one on the other side, make sure it's actually in the base. And then finally signal 4 through the resistor, all separate resistors, remember, out of there into the base. So now we have our signals connected. So now we connect the power. So I'll connect positive power into the collector of the top left transistor. From the emitter, I'm going to connect over here to the load. We'll say this pair here is the load, which is where I have my oscilloscope probes connected. They will be the load, a 10 mega ohm load, in fact. So that same side of the load connects to the collector of the bottom left transistor, and from there out to negative of the power. And then the same thing on the other side, positive into collector of top right, emitter of top right, into the right side of the signal, the load, from that same side to the collector of the bottom right transistor, the emitter out of there to negative. Let me get my oscilloscope warmed up, and I'll go ahead and get my power supply on as well. So there's one more piece to the puzzle, which is, of course, the signals. So I'm going to say this positive here is signal 1. Signal 1 connects to transistor base 1, that's the top left. Signal 1 also connects to the bottom right, which is 4 here. So the top left and the bottom right is one path. And then the second signal will go to transistor 2, which is the bottom left, and the second signal will go to transistor 3, which is the top right. So a diagonal one way, a diagonal the other. One will get high, one will get low. So I'll simply have a wire for positive, which I'm going to leave loose right now. That's going to be my on, my high, my 1, and the ground will be low. So I'll leave that one loose as well. So now, of course, the oscilloscope is showing nothing because it's not connected to power yet. It's in there, but it's not connected yet. It's got loose signals. I'm going to go ahead and turn the current limit up here to 10, 20, 30, 40, 50, let's say. And of course, it's drawing 0 amps because none of the transistors have current going through the bases, which means they're closed off, fully blocking the voltage. So I will go ahead and connect the 0 signal first, because that will still not turn any of them on because I'm doing this live. So let's do it in a way that won't give us nonsense. So I will connect the second signal here, will be 0. Now, nothing happened, of course, but now I'll connect the first signal as 1, and suddenly, I suppose you can't see that, can you? There we are. So running it at 5 volts, and here, the 0 line is here, and the divisions are 2 volts, so we've got 2, 4, and a half is 5, roughly. Let's measure more precisely. So if I have my actual multimeter here, so I'll temporarily unplug the oscilloscope, and you'll notice that it's still drawing current here, because it's turning the transistors on and off and power's going through them, or trying to, it's the base current. Nothing's going through the load connection, but it is going through the transistor, let's see, which one would this be? This would be the bottom right transistor, because we've got a signal high on its base, and then its emitter is connected to negative. So that's basically just base current and nothing else. Since the load was 10 mega ohms, there was very little current drawn. I'll put it back in and show you. See, very little at all is actually going through the top left transistor because the load is only letting through whatever 10 mega ohms will let through. So the top left transistor is basically choked off. So let's measure with the multimeter, and we get 4.52 volts, which is not 5, but it's fairly close. Let me see if this works with both the oscilloscope and the multimeter plugged in. And indeed it does. The power of high impedance. So we're getting 4.52 volts, which is up here. Now if I switch the signals, if I put it the opposite way, plug the ground in first, then plug the signal in, you can see minus 4.52, and now it's down here, so 0, 2, 4, and a half. And that's the H-bridge. That's it. 4 transistors, 4 resistors, if you're using BJTs. That's all you need. Now, it's messy and it's wasteful. If you're trying to drive an actual robot arm or something, you can purpose build a better H-bridge using MOSFETs, incorporating your flyback diodes. You can do PWM, all kinds of things. But since I'm just starting out, I'm trying to build up a nice set of beginner, useful circuits. This is an H-bridge. Flat. It is. I don't have to worry about power consumption because I'm plugging it in the wall, or I have plenty of batteries, they're cheap. I'm not trying to build a commercial device here. So what I have, and what I'm going to have when I finish soldering, is just straight up an H-bridge on a board with 2 pins. I don't have to think about it. It's just got 2 pins, plug in your load, 2 pins, done. So I can test it with making a signal generator, I can test it with motors, I can test it with anything I think of that is bidirectional current. If I want to make an indicator LED, right? You can make an LED that, let's say, is green for transmit and red for receive or something like that. So you have one LED facing one way and the other LED facing the other. If I want to build that and test it real quick, plug it into the H-bridge, and I'm done. See? It's just sitting on a shelf anytime I need it. That's great. But let's actually do something more interesting. Let's go ahead and turn off the power supply. Let's connect it to the oscillator. So I no longer need the connection to the power supply. Or rather I do, because I'm being dumb here. Hold on. The oscillator is going to supply the signal, not the power. The H-bridge will have its own power plug, so let me fix that. Now that there's no signal, it's going to show 0 amps. There we go. So this is the H-bridge power. The signal is completely disconnected. So now let me get my oscillator, which I have not mounted yet. I live in an apartment and it's winter, so I don't want to go out every day cutting wood. I'm going to do them in a batch, especially since it's loud. I have to go outside in the backyard to run the jigsaw. But anyway, here's my oscillator. So I'll just put this down somewhere convenient. My mess is migrating. I'll go ahead and leave it unplugged for the moment. So I will take one wire and I will connect the negative. Here, I'll put it over here so you can see it. Try to not rip these wires loose, they're not secured yet. So I have the ground connection, and this I need to do as a shared ground with the power supply ground, because the signal goes in the base of the transistor, comes out the emitter, and the power comes in the collector, goes out the emitter. So this is essentially, by conventional current, the return path for the base current. And since this is going to be oscillating quickly, the multimeter will no longer be useful, so I'll put that away. The multimeter measures only stable signals. Fast-changing signals, that's why we invented the oscilloscope. So I'll just move that up there, out of the way. So now, very simply, we just connect our two signals. One collector goes into the positive, one collector goes into the negative. I'm simply swapping the signals. And now, of course, it's still acting as an antenna because there's no power going through it. I will plug it in. If I can find the cable I've already lost, it's already buried. Here we go. So I'm plugging in the USB cable of the oscillator. That was easy. Recognize the wiggle? And it's funny the way it manifests. It's only on the bottom. That's fascinating. So it's only when it's giving the negative signal the way I have this plugged in. So what if I flip these wires? Let me just flip the signal wires, and it's on the bottom again. Very interesting. If I have only one signal wire plugged in, of course there's funkiness, but no matter how I flip the inputs, the wiggly is only on, in this case, the negative 4.52-ish side. And you can see this is the average current being drawn back and forth, back and forth. So now it's down to 0.007, 0.008, probably because it's spending some of its time switching. I'm not sure, I'd have to analyze, but in any case, the circuit works. Here's the 0. In fact, we'll make sure, yes, there's the 0. So we go up to 4.5, to 4.5, so about 4.5 volts each side. And then let me expand, let's see. Yes, so if one wave starts here at a top left corner, the next wave is here. So 5 milliseconds is the division. So 5, 10, 15, and then a smidge makes 16, which is about 1 divided by 60. 60 hertz. But I am fascinated why that's only on the negative side, no matter how I have it hooked up. And of course, if I flip the oscilloscope probes, it'll end up being the same thing. Only on the bottom, even if I flip the oscilloscope probe and measure the voltage the other way. I don't know. It is possible that it's some sort of interaction with the oscilloscope. Maybe. I would love to speak to an actual electrician about that. But in the meantime, simply put, it works. The oscillator is supplying the signal. Now, the enterprising people out there will say, why did you even do this? Reason number one is, of course, the same reason that Jim Kirk climbs a mountain, because it's there. But perhaps more usefully, it's a learning opportunity. I even learned something when I was recording yesterday's video and had to scrap a whole bunch of it because I realized I was explaining something wrong because I understood something wrong, despite the fact that the circuit worked. Just because your circuit works doesn't mean you know why. But I think now I do, so we're good. But like I said, a learning opportunity. You learn about H-bridges, you learn more about soldering, you learn about the interaction between circuits and power supplies and how you can hook up multiple power supplies and make sure to draw off as if it's a power supply without shorting anything out. Also, for various upcoming projects, it's useful to me to have an oscillator that runs at 60 hertz. It's also useful to me to have a modular H-bridge and a modular filtering set. I guess capacitor ladder would be an appropriate term. And it's useful to have a modular amplifier. It's useful to have all of these things separate. Modular. I love modular. They even make power supplies in computers modular now. Back in my day, you had a giant anaconda of cables that would spray off and you had to hope that you could get the rest of them out of the way. Now you just plug in what you need. It's like magic. But the main thing is people will say, you're trying to get a square wave, right? That's right. I'm trying to take a DC stable signal, turn it into a square wave, and filter it to a sine wave, and then feed that sine wave into an amplifier. But your oscillator puts out a square wave. It sure does. But it puts out a square wave from 0 to 5. This one puts out a square wave from -5 to 5. But then why don't you just put 10 volts to the oscillator and use a capacitor to remove the bias to get -5 to 5? If I were making something, I probably would. But like I said, this works great with separate boards. I wanted separate boards anyway. It's useful to me to have an oscillator that I can use without an H-bridge, and an H-bridge that can take any input, not just an oscillator. So by having them separate, I'm serving my future. And in that point, well, why not just do it this way? I've already got the boards, or I have one of them at least. Why create something separate to overpower and filter the oscillator when I can just stick it in the H-bridge and it's done? There you go. And plus, this changes the voltage a lot easier. I'm only running 5 volts, or whatever volts, if I turn up the voltage, let's say 9 even. I'm setting that voltage to these transistors. But in the oscillator to get the voltage swing I want and then filter it, I'd have to run double that voltage. So I could get a total higher swing, peak to peak, 10 volts peak to peak with only 5 volts, 24 volts peak to peak with only 12 volts. But I would have to put 24 volts through the oscillator. These transistors could definitely take that amount of voltage forward, maybe not backward, because remember, the transistors in the oscillator have to suffer a very large negative voltage. So maybe that would be too much for them at that point. But also, I would have to be much more careful to limit the current. So the real answer to why, not just this, but in general, the answer to why is because it suits my purpose at the moment. When you're working for a company and you have a boss and they have projects and deadlines and all this other nonsense, you gotta go with whatever the head engineers decide. And then the bean counters direct them and blah, 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 blah. But this is the joy of hobby. Who's my boss? That's me. And my boss said I should do it this way, so by golly I did, didn't I? I want to make my boss happy. So while I go do that, I'll be seeing you.